Okay guys, welcome to section 8.2, pairwise comparisons and inference after ANOVA. Alright, now I want to just admit up front that this is not going to align terribly well with what's in the text. The text doesn't go very far at all on the pairwise comparisons. They make reference to things, and it's in keeping with the approach that they're taking. What I'm trying to do is at least give you a little bit more exposure to some of the kinds of multiple comparison procedures that come up. I think if you're working in the life sciences, especially in experiments where you're making multiple comparisons, it's something you ought to be aware of in a rather significant, if you'll excuse the bad pun, but a rather significant way. Maybe in summer research that you work on or would like to work on, or other projects. Research studies will often make reference to adjustments for multiple comparisons or post hoc comparison procedures. And I just think it's something that you really should know something about. So I'll try to flag the basic approach that the text uses, but then introduce you to a couple others so at least you're aware of, and you should know that R can do just about any comparisons you'd want to do. You just might have to Google the particular package and look at a couple of examples, but you can do that now. You've climbed the hurdle to learn about R. You've climbed the hurdle to learn some statistical inference, understanding p-values, understanding confidence intervals. So now all these other procedures become accessible to you with a little bit of work. All right, so let's have a look. All right, so our approach here is a little bit of ANOVA review and then talk about follow-up tests. So Fisher's LSD method is the one that appears in the text, sometimes by name and sometimes not necessarily, but this is in the text. These two, I believe for the most part, are extensions. I know there are references or brief references to them, but that's not really covered in this section. So let's get going. So just to review, we've got these required conditions for ANOVA: independent samples, normal, each of k populations, or it might be a randomized comparative experiment. The response variable in each population is a normal distribution, and the standard deviations are indeed equal, or at least cannot assume that they're not equal. All right, so here's the problem, and then we're going to think about the solution. So the problem is you do an ANOVA, and you find out that there's evidence of a difference. But now you've got 5 different groups or 6 different groups, and where are the differences? So multiple comparisons using separate 2-sample t-confidence intervals to compare multiple pairs of means renders the nominal confidence levels of the pairwise comparisons invalid. Right? If all pairwise intervals are computed at the 0.95 level, the chance that all intervals contain the corresponding parameters will be much less than 95%. So let me just take a quick crack at that. So think about tossing a coin. We all know the chance of getting a heads, if it's a fair coin and we're just flipping, is going to be 1/2. Chance of getting a heads the second time is 1/2. I hope you're willing to assume those are independent. So the probability that they both come up heads is 1/2 times 1/2, which is 1/4. Okay, so if you toss 2 coins, you expect each one to have a 1/2 probability, but if they're independent, we can multiply. And that's key, because we can think of these confidence intervals as flipping a coin. It's just that this coin has a 95% chance of coming up heads, that is, of covering the parameter. And the parameter might be a difference in the means. But if we take that 0.95 and say we have 5 different groups that we want to compare, well, it turns out that if you take those 5 groups and take 2 at a time, we've got 10 different comparisons we could make there. So if we take 0.95 times 0.95, well, I don't want to write all that, so we'll just do 0.95 to the 10th power. Notice now that the probability is 60%. 60% what? That 60% is the chance that all the intervals are right. So we started out saying we have 95% chance that our interval's right. It's a 95% interval. Now our hit rate is only 60% of being right for all our intervals. So it sort of feels like false advertising. And it can be very misleading. And on the significance side of things, if we do 0.05 tests repeatedly, the chance of making a mistake somewhere along the way, well, 0.95 is the chance of making a mistake on the first test, 0.05 on the first test, but not making a mistake is 1 minus 0.05. That is not incorrectly rejecting the null hypothesis. And so if we do that repeatedly, we're back to the same problem where we have a pretty small chance that we haven't made a mistake somewhere along the way. So the way we can approach this differs across the different methods that we'll consider. But that's the basic problem. So if all pairwise intervals are computed at the 95% level, chance that all contain the corresponding parameters will be much less than 95%. So the solution is, first do the ANOVA, carry out the test that all population means are the same, and get the F statistic. Remember, that's the mean square of the groups over the mean square error. It's a variation among the means over within the sample. Okay, so we find out that there's a difference. Where are the differences? Well, that's the idea of follow-up procedures. Okay, so multiple comparison procedures. If the global F test rejects equality of means, we want to use multiple comparison. Post hoc follow-up methods, it has lots of names. We want to calculate simultaneous confidence intervals or carry out hypothesis tests where we're making some sort of adjustment for the fact that we're doing lots of procedures. All right, so there are two methods that are described in what follows. Actually, I lied. There are three methods described in what follows. Must have been a previous edit that I didn't catch. And so the last is going to be Tukey's method. Same Tukey that came up with the dot plot and the box plot. It's like turkey without the R. Well, where's the R? Well, it's being used for the software. Sorry, bad dad humor. So Tukey's method, and that's the one actually that R can be done. That can be done without even blinking. With R, you can do that one quite easily. The others as well, but just differently. So all can be done using output from RStudio, so let's have a look. Now, Fisher's least significant difference method is essentially the methods that's discussed in this section. The Fisher's LSD method is really just an extension of the two-sample T procedures. So remember, for the two-sample T, okay, let's compare this with what we've done so far. On the two-sample means, when we're comparing mu1 minus mu2, we use something like this. Now, well, it was this interval. Now, if we were to assume that the standard deviations were the same, we'd get something like this. Now, we didn't have to assume they were the same when we were just comparing two groups, but when we're comparing more than two, it's much simpler to just go ahead and make that assumption. So this will both be this pooled standard deviation, the square root of MSE that we got. So those will be the same, and then when we take it out of the square root, we get a common factor. So that's the square root of MSE. Well, let's not go there yet. We could just call that SP. That's called the pooled standard deviation, 1 over N1 plus 1 over N2. So that would be if we just had two groups, mu1 minus mu2. But in the ANOVA case, this is going to be based on K groups. Why? Because we get a better estimate of the standard deviation by pooling them all together. And that's what we talked about with the MSE as part of the analysis, the mean square error. So this is the approach that we would use for the Tukey's LSD. So let's go back and take a look. So the T star is the multiplier. This S sub P is going to be the square root of the MSE. And then we're going to use the T with the appropriate degrees of freedom with area alpha over 2 above T star, or actually what we can see is that here's our T star, and here's our negative t star. So the area inside is 1 minus alpha, or our confidence level. So if we wanted to be 95% confident, we'd be looking for something like XCT of 0.95 and the degrees of freedom equal to whatever it was. And that would be our multiplier. Okay? So I want to point out at this point that all the situations or all the cases that we look at are going to have the same form, all three methods. And it's going to be like our stat, and our stat is a difference in means plus or minus. Well, we had margin of error before. It's going to be a little bit more, we'll have a critical value of some sort, and here it's t star. We'll have the square root of the MSE showing up, just as it does here, and then we'll have the square root of 1 over n1 plus 1 over n2. So really the only difference between Fisher's, Bonferroni, and Tukey will be the particular critical value and kind of what conditions we're imposing to get to that. All right. Now I should note that in this section there's also some focus on test of hypothesis rather than confidence interval. To kind of see how all these pieces fit together, I prefer to focus on the confidence intervals, but let me just give you a quick glimpse of how this would look from a hypothesis test perspective. We'd just be doing as we did before, right? We had this test statistic, and the general form was a statistic minus a null parameter over a standard error. Okay, so they had that form whether we're dealing with proportions or means or difference in means. We had either a t or a z over here. Well, now we're going to have a t. And for Fisher's case, the LSD, or the sort of the standard method, and this isn't too bad if you're planning a particular set of comparisons like we are with the mice data, because we're not fishing for results. We're actually intending to test some particular methods or particular differences. So we want to compare groups I and J. So we take the difference. The null parameter is just going to be 0. And down below is the standard error. Well, the standard error in this case is going to be our square root of MSE times the 1 over Ni plus 1 over Nj. That's all. And that's going to have a t distribution, and the degrees of freedom are going to be the n minus k that we saw before was the error degrees of freedom. Okay? So that is to say that you could go ahead and compute this test. It would look similar to the ones that we've done before, but it's going to take all the information from all the groups to get a better estimate of the standard error. Now let's go back to our setup here and move on to the next method. The Bonferroni method is really a general method for multiple comparisons. It's trying to just explicitly adjust the overall comparison level or the comparison rate, or either tweaking your confidence level or tweaking the alpha level to account for the fact that you're making lots of comparisons. It could be used if you were computing lots of correlation coefficients, or if you were doing lots of regressions. It's a very general philosophy or approach, so it tends to be conservative because it's not optimized for the particular setting of comparing 5 groups or k groups with a particular assumption of the data being normal. So it can be applied whenever multiple significance tests are being carried out. The basic idea is to get C confidence intervals with simultaneous confidence level 100 times 1 minus alpha % confidence. So we're making C comparisons. So before I mentioned 10 comparisons if we had 5 groups that we were comparing. So C would be 10 in that case. And so we want an overall confidence level, kind of a family-wise level it's sometimes called, to be 100 times 1 minus alpha. So if our alpha was 0.05, let's go look for our mice. Let's see, maybe they're over here, right? So we had, in this case, we had 6 groups that we're comparing. So we had 6 times 5 is 30 divided by 2, that would be 15. So if we did all possible comparisons, that would be 15. But if we only wanted to make the particular comparisons that we had planned to do in the initial setup, here it is. So we were planning to do 5 different comparisons in that case. So in there, our planned comparisons would actually be 5. So it really depends on the specific situation. You may be just trying to compare everything with everything, and the formula for that is to take the number of groups, k times k minus 1 over 2. That's one of those annoying formulas that Gauss discovered when he was like 5 years old or something. But it's a very useful formula for figuring out how many pairs you can get from k items. So that would be 15. So, but if it were less stringent, then we'd be using 5, and we'd be taking 0.05 divided by 0.01. So let's take this case where we actually just want to do 5 different comparisons. Then we could say let alpha equal to 0.05, and then we would test each one at the 0.05 over 5, which is a 0.01 level of significance. Okay, and if we were doing a confidence interval, we would again divide the alpha by c, so we'd have 1 minus 0.01, so we'd be using a confidence level of 0.99 to obtain an overall 100 times 1 minus 0.05, or 95% level. Each comparison is going to be done at the 99% level in that case. All right. So here's an example. In this example, we're only interested, yes, this is the one that I was telling you about, the 0.05 over 5, or 0.01. If we wanted to just compare groups 1 and 2, we could either carry out a test or compute a confidence interval, and we could go ahead and fill in some numbers. And let's see if we can track those down. All right, so we have, we'll take mean 1 and mean 2, so 39.68. Yes, I believe that's the order that I wanted to go in, right? Okay, yes. So 39.68 minus 32.69. And down below, we've got SP, which is the square root of the MSE. So let's see if we can track that number down. Now for that, we need the ANOVA table. So I'm going to run those commands above, but we're not going to actually need them. What we need is the ANOVA table, right, that we got by taking ANOVA, the model. And so here we have the MSE is 44.6. So that's the thing that we're going to need. So the square root of 44.6. And then the sample size is for these two groups. So they were up here. 1 over 56 plus 1 over 57. Now we could have R do these calculations, but at this point in the course, it's nice to get our hands dirty a little bit and make sure that we know what's happening behind the scenes. So 39.68 minus 32.6, and I can't read my writing, I guess it was 9, divided by the square root of 44.6 times square root of 1 over 56 plus 1 over 57, and we get 5.56 showing up. So 5.56. So we could get a two-sided level of significance there. And so the two-sided level of significance we would compare with 0.01. Now this is hugely extreme, so we should be pretty sure that no matter what we do to adjust that, we're not going to have we are going to have a significant difference between those two groups. So if we go over to R and we find our command line, we can just go ahead and do that. Okay. So what do we want to do? We want to take 1 minus PT, and get the, or if you like, XPT, get the probability in the upper tail for 5.56, and the degrees of freedom was n minus k, so that was 349 minus 6, so that was 343. Okay, so 343, and as predicted, this is super small, it's way out in the tail, so 0.0000, it's going to be significant, certainly at this more restrictive 0.01 level. So we've carried out a first Bonferroni test. We made the adjustment, so we'd call this a overall 5% significance level test, but each comparison is being compared, each p-value is being compared to the 0.01 level. So that's how we've adjusted for the multiple comparisons. Now, if we had done this with the T procedure, an unadjusted procedure, the Fisher's method would have, in this case, calculated the same test statistic, but we would have been comparing the p-value with 0.05. Now, because the p-value was so small, it doesn't really matter which in this particular case, but that's the idea of the procedure. On the confidence interval side, let's have a look. So we'll copy over 39.68. So the difference, 39.68 minus the 32.64. We've got the square root, we've got SP is the square root of 44.6, but we calculated that last time, so let's go ahead and just get that number. So we've got it handy. It's the square root of 44.6 of a 6.68, so 6.68. So we've got plus or minus something times 6.68 times the square root of 1 over, was it 56 plus 1 over 57? Notice that this piece is the same as what we're using in the denominator over here. So we could have kept it around for reuse, reduce, recycle, all that. And then we're going to put in an appropriate t value. Okay? So the t multiplier now, we're going to have 0.99 in the middle. And we can use the XCT. We don't really need the X unless we want the plot, but just to make the point, DF is 343, and that will give us the right multiplier. Because the sample size is quite large, I know it's going to be close to the 2.58 figure that we see for a normal curve. Now, I'm not assuming that you just have that at the top of your head, but 0.99 and DF is 343. And we get 2.59, so a little bit more than the 2.57 that we would have gotten if we were using a bell curve, a normal curve. But 2.59 is correct, and it's adjusted. So if we use this interval for every comparison of the 5 that we were going to do, then we'd say that overall we're 95% confident that all of them are correct. So the overall confidence level is 95%. Every pairwise interval is going to be 99%, right? So I did this one. So after I get done with all 5, we'd say overall we have confidence that, not that 95% is correct. We have our overall confidence level is 95%. These are 95% simultaneous confidence intervals. So we're 95% confident that they all contain the true intervals, or the true parameters. Okay, so let's take a look at the R code on this. Right. So I've looked at the output, and I think we've got what we needed to get from that. I was trying to remember if I had any other commands in here that would address it, but no, I think I showed you the calculations we did at the command line. We used the information here to go about doing those calculations. Now, Tukey will rely on R a little bit more to do some of these. Oh, I'm sorry. I actually do have the calculations down here. I knew it was around here somewhere, but you can certainly use that to go ahead and get the values that you need. Here's a typo, so hopefully that'll be fixed by the time you see this. So that was the middle proportion and then the multiplier if you were doing all 15 comparisons. Okay. let's get back on track for our last method. So Tukey's pairwise multiple comparisons method. What this is doing is really tailoring a solution that's specific to the situation of carrying out an ANOVA with the normal assumptions, with sample sizes, all that. Now the Tukey method assumes that the samples are pretty close to each other in size. So it takes the number of comparisons into account, and we're going to replace the t star by another critical value based on the distribution of the difference between the largest and smallest of a set of k sample means. Now I'm going to show you a few pictures that will hopefully at least suggest the idea of what's going on. It's a little bit technical, but let's see if we can make some sense of it. So I'm going to put this away here and open this one. It's an R script, so it's not an RMD file per se. It's got just R commands, all right? So it would be like one big chunk. But it's a series of simulations. So what are we looking at here? We're looking at cases where the means are actually the same. They're all 10. Standard deviation is assumed to be 2. Sample size is 5 for each of the groups. And I'm going to run 10 to the 4th, so 10,000 trials where we generate 5 samples of 5 from each of 3 groups. We're going to compute the means, compute the difference, and look at 2 particular things. And so I'm hoping by the end of this it will make sense what I'm getting at here. But the first is just compare group 1 and group 2 and see how big that mean is. That's just for one particular group. But then we're going to look at the comparison between the largest and the smallest mean. And what we're going to notice is that the more samples that we compare, we're starting with 3, we're going to move up to 5 groups that we're comparing. The more groups that we're comparing, the greater the chance of a big difference. And that makes sense, right? Intuitively, the more chances of getting a great result, right? I mean, isn't that why you take the an exam or an SAT? Some people take the SAT multiple times because just by chance they're hoping to get at least one really good result. The same sort of idea here. The more groups that we're comparing, the more chance of an extreme difference. So without further ado, let's run the first part of this, and I'll try to explain what we're looking at. Okay, so the first is just the comparison between group 1 and group 2. And so it's an absolute difference in the means. And so we don't often see a difference much more than 2 or 3. Whereas when we compare the largest with the smallest, that tends to be bigger because we're not just comparing 2, we're sort of implicitly comparing all 3. And then that tends to be larger. Now let's go back and move up to the case with 4 groups. So rather than just 3 groups, now we've got 4 groups that we're comparing. And let's get a plot just like this one. And notice that this shifted over. This one didn't change much, right? And I think I can go back here, right? So this one, in terms of its extremes, didn't change much. But when we compare the largest to the smallest, you'll see that's shifting out. Right? The more groups, the greater the chance of a large deviation or a large difference. And this plot looks at those 2 directly. And we see that this one, the second set, is higher than the third. Now let's go all the way and do it with 5 groups and see what happens. So I'm going to run all of these at once, and then we'll focus on the last comparisons. Okay, so comparing 3 groups, 4 groups, and 5 groups, the range, this is called the studentized range distribution that underlies this, is going to be greatest with 5 groups, smallest with 3 groups. More groups that you compare, more chance for a large difference. And what I've printed here are kind of the 95th percentiles for each of these, and they really just say what this picture is showing us, that large values for the difference are much more likely when we're comparing a lot of groups, like 5, rather than just 3 groups. Again, this is implicitly comparing all the combinations within. So when we're comparing 5 groups, we're sort of thinking about there being 10 underlying comparisons that could have been large. All right, so now back to our situation. So hopefully you're convinced that this is another way of looking at the problem of multiple comparisons. You have more chances for a big difference. So the multiplier that we get now that Tukey derived that takes that into account comes from what's called the studentized range distribution. It still has the SP, it still has this, as I told you at the outset, we still have the statistic, and we could reframe this as a hypothesis test, but for now we're looking at it as a confidence interval, the difference in the two. Right? Hypothesis test, you could always look and see whether 0 is inside the interval. But Q star is the upper alpha critical value from the studentized range distribution with parameters k, that's the number of groups that we're comparing, and n minus k is the error degrees of freedom. So those are the arguments that you would put in. You can see the R command down here. You're putting in 1 minus alpha, so the level of confidence, 0.95, 0.99, whatever you want that overall level of confidence to be. So with Bonferroni, we had that family-wise level was 95%. That's the same thing we do here. 6 groups, error degrees of freedom 343, and we can get that from R. So let's have a look. So if we copy this over, now I've got it in the code as well, but I just wanted to show you at the command line, then the multiplier we get is 4.05. But we take that 4.05, and to get it on the right scale, we divide by 2. And that has to do with the fact that we're comparing 2 groups here in each in the pair. So let's see what that was again. 4.05 divided by the square root of 2. So let's see if I can fit it in here. 4.05 over the square root of 2. And what we get here is we get 2.86. So that 2.86 is bigger than the T multiplier, but not as big as the Bonferroni multiplier typically. Okay, so it's sort of somewhere in between, and it's more optimized or more tailored to the particular situation that we're considering. Okay, now let's see how we could do that with R. Go back over here to this that well, not this one, right? Wanted to go back to the mice diet case. And let's see, we will pretty much at this point, we can let R actually do that for us too. So if we let R do it for us, we would just run Tukey HSD, and it would go ahead and compute the upper and lower endpoints, the difference in the lower and upper endpoints for the 95% family-wise level, and it would give us a p-value for each of these comparisons. So that's really baked into the core of R, and then you can often plot it because often that's useful. Problem is we can't see the labels in this particular case, so I showed you how one could actually rotate the labels and fit them in, just to show something a little bit beyond, but that's the kind of thing you might do if you were putting together a paper and you wanted to show all the comparisons. You can order them also so that all the differences are positive, right? Taking the larger minus the smaller in each case, and that can make it a little bit easier to look at. But what you'll notice is that a few of the intervals contain 0, quite a few don't contain 0. So with those sample sizes, we're able to detect quite a few differences among the means. All right, now also remember I had the R commands handout, so make sure you have a look at that as well. So in this section, I looked at another example there for how to do some of these procedures with the ANTS data, and I worked out some using the T-star, using the specific commands. So you have those as examples to refer to. All right. All right, now let's go back and see that was the confidence intervals. We could have also done it with the hypothesis test. In this case, we would just let R go ahead and take care of those hypothesis tests for us. But we could certainly do those ourselves as well and find the p-values as needed. Okay, so to summarize, I've showed you 3 methods. Fisher's LSD method is the most liberal, and it's generally not advisable unless you have specific plan comparisons that are really justified by previous research. So we're confirming, in a sense, whether or not there's a difference in the new study. Bonferroni's method is good when you don't know what else to do. You want to be conservative. You may be doing lots of comparisons, a little bit of fishing for significance. A middle ground that's good is this Tukey's method because it's tailored to the situation, and it's best when you're doing all possible comparisons. Now, if we were just doing 5, let's say, as in the mice, maybe the Bonferroni's method that makes that adjustment is going to be fine. There are other methods, the methods that I've talked about when I've taught this class. It sometimes depends on the text I'm using. One of the names you'll see is Chaffee's method. That actually takes into account all linear combinations, which is a bit more general than pairwise combinations, because it may be that you want to, part of what your expectation is that you want to compare the average of 2 groups versus the average of another 2 groups, or compare all the groups with the control group. That's another one for which there's an optimal test. That's called Dunnett's. Dunnett's, and then there's Duncan's, and you'll just see a whole bunch of them. And I'm sure if you look at Wikipedia, post hoc or multiple comparison tests, you'll see quite a few. And what's going to happen usually is you'll end up in a research lab somewhere on a project, and everybody's going to say, well, we always use this test or that test. And at first you won't know, but you'll have the basis to learn about that. And then you'll say, oh yeah, that makes sense because it's making this adjustment for multiple comparisons. All right, so that's all on this section 8.2. Now you'll notice that the problems that I've assigned for warm-ups that I'll do, that'll be the last warm-up assignment, don't tie much into this Tukey method and Bonferroni. They're really focused on the Fisher method that's discussed in the text. That's okay. But I wanted you to at least be exposed to and have seen these other methods. Again, so you'll be able to hit the ground running wherever you next land with the opportunity to use some of your biostatistics training. So take care, and thanks for listening.